Hello everyone, this is Miss Haneen Khair from Al Shumukh International School. In this video, I will explain standard redox potentials, standard hydrogen electrodes, and standard conditions. Magnesium atoms or any other metal tend to shed electrons. Metals always tend to lose electrons and go into solutions as magnesium ions. As you can see in this diagram, magnesium ions are formed and electrons will be left behind on the surface of magnesium. In a very short time, there will be a buildup of electrons on magnesium, and it will be surrounded in solution by a layer of positive ions. The positive ions in the solution are attracted to the layer of the electrons present at the surface of the metal. Sometimes this attraction is strong enough so that the positive ions reclaim their electrons and reform the metal. A dynamic equilibrium will be established when the rate at which the ions are leaving the surface is exactly equal to the rate at which they are rejoining. At that point, there will be a constant negative charge on the magnesium ion and a constant number of electrons of ions present in the solution. So the number of electrons at equilibrium is not changing. As you know, at equilibrium, the amount of the reactants and the products are constant. So there will be a constant number of electrons at the surface of the metal and a constant number of the magnesium ions or the metal ions in the solution. Copper, on the other hand, is less reactive and so forms its ions less readily. The ions that do break away very quickly grasp their electrons and reform the metal again. So therefore, there will be less charge on the metal and fewer ions in the solution. Measuring this charge will reflect the reactivity of the metal. If we find a way to measure how many electrons or how much electrons do we have on the surface of each metal, then this can reflect the reactivity of the metal, how reactive the metal is. In both cases, there is a potential difference between the metal and the solution. However, the potential difference generated in case of magnesium is higher than that in copper because you have higher charge in magnesium rather than in copper. The absolute potential difference is the potential difference between the metal and its solution. Unfortunately, this potential difference is impossible to measure. It would be easy to connect one terminal of the voltmeter to the piece of the metal and the other terminal to another metal that has its own potential difference. So what you are actually measuring is the potential difference between the two pieces of the metals rather than between the metal and its solution. The way to solve this problem is to create a reference electrode to which we can compare all other metals. And we need to do this at standard conditions. Now, what do we mean by standard conditions? The pressure of the gases has to be at 100 kilopascals, which is equivalent to 1 atmosphere and 1 bar, just different units. The temperature at which you're carrying out the experiment has to be 298 kelvins or 25 degrees Celsius, and the concentration of ions in solutions is equal to 1 mole per decimeter cube. Standard electrode potential and standard redox potential means the same thing, in case you saw them. All the reactions involved in measuring standard electrode potentials are redox reactions. Electrons have to be involved. Loss and gain of electrons at the same time. The reactions involved are equilibria. By convention, they are written with the electrons on the left-hand side. So we always start with the metal ion gaining electrons to form the metal. Mg2 plus 2 electrons forming Mg, Cu2 plus 2 electrons forming Cu. This is by convention. The reference electrode. What is the reference electrode we are going to pick? It's called the standard hydrogen electrode. This electrode consists of hydrogen gas at a pressure of 100 kilopascals, just to satisfy the standard conditions. It's bubbled over a piece of platinum foil, dipped in a solution of HCl or H2SO4 with the concentration of H plus 1 mole per decimeter cube and at a temperature which is equal to 298 kelvins. Now, of course, in the couple H plus H2, we don't have a metal. So how electrons are going to be conducted? We need to use a metal, an inert metal, unreactive metal. That's why we use platinum. The surface of the platinum foil is covered with a porous platinum in order to increase the surface area so that the reaction can take place more quickly. The equilibrium between H plus and H2 is established more quickly. This is how we represent the reaction. H plus 1 electron, it's going to give half H2 gas, comma platinum, because platinum is part of this half cell. The electrode potential of this half cell is assigned a value of 0.0. Because it's the reference, it's considered to have a value of 0. We can connect any other half cell to the standard hydrogen electrode and measure its own electrode potential. In order to measure the standard electrode potential of any metal ion and a metal couple, the latter is connected to the standard hydrogen electrode. So for example, in this case, you have a Cu metal electrode dipped in a Cu metal ion. Again, the concentration has to be 1 molar just to meet the standard conditions. This half cell is connected to hydrogen half cell, standard hydrogen electrode. Again, the hydrogen gas, the pressure is 1 atmosphere. The concentration of the solution of the acid is 1 mole per decimeter cube and the temperature is 298 kelvins. The two half cells are connected via a salt bridge that contains KNO3 or any other electrolytes, and the two electrodes are connected using wires to a voltmeter. The electrode in the hydrogen half cell is platinum. The standard electrode potential E0 of a half cell is the EMF of a cell containing the half cell connected to the standard hydrogen electrode. So, for example, the E0 of gold, it's plus 1.692. So if you connect gold to a standard hydrogen electrode at standard conditions, the voltmeter will read plus 1.692, which is equal to the standard electrode potential of this half cell. Similarly, we can measure that of silver, copper, iron, and any other metal. The half cell with the more negative E0 is placed to the left, which acts as the anode. The half cell with the more positive E0 is placed to the right, which acts as the cathode. When the cell is in operation, electrons always flow from the anode to the cathode. So now this will give you a hint which metal or which half cell has to be placed at the anode and which half cell has to be placed at the cathode, but just comparing the values of the E0s of the each metal and metal ion. The sign of a standard electrode potential is fixed and doesn't change if the equation for the half cell reaction is reversed. So whether it's a reduction or an oxidation, whether you write the equilibrium as Zn2 plus 2 electrons forming Zn, or as oxidation of Zn, the value of the E0 of this half cell is constant. It doesn't change the sign. The standard electrode potentials are sometimes referred to as standard reduction potentials, which are the tendency for a chemical species to be reduced. And it's measured in volts at standard conditions. The more positive the potential is, the more likely the substance will be reduced. By reduced, we mean gaining electrons. So if the value of the E0 is more negative, this means that the metal is more reactive and has a higher tendency to lose electrons. If the value of the E0 is more positive, this means the metal is unreactive and the metal ion is more reactive and it can gain electrons more quickly. So as you can see in this electrochemical series, reactivity series, the value of the E0 is going from 2.87 for F2 F minus. So we notice that F minus is a very weak reducing agent, whereas F2 is a very strong oxidizing agent. However, lithium with an E0 value of negative 3.04 volts is a very strong reducing agent, and lithium ion is a very weak oxidizing agent. Now, how to measure the E0 of more complicated systems, like nonmetals and their ions in the solution, such as Br2 and Br minus, iodine and I minus. In these cases, just like in H2H plus couple, we don't have a metal to conduct the electricity, so therefore we need the platinum electrode, the platinum metal, just to ensure the flow of the electrons through the cell. So as you can see, half Br2 gaining 1 electron forming Br minus, E0 is positive, therefore Br2 has a high tendency to gain electrons, and therefore it is a good oxidizing agent. Similarly, iodine plus 1 electron forming I minus is positive, but not as positive as for the Br2 Br minus couple. Therefore, Br2 is a better oxidizing agent than I2. Another example of such systems is Fe3 plus Fe2 plus. As you can see in the diagram, the Fe3 plus and the Fe2 plus ions are present in the solution at a concentration of 1 mole per decimeter cube, and the electrode is placed to the right. We need a platinum metal to ensure the flow of the electrons. On the left-hand side, you have the standard hydrogen electrode, with the hydrogen gas being pumped at 1 atmosphere pressure, and the concentration of H plus in the solution is 1 mole per decimeter cube. Electrons will flow from the anode to the cathode, from the negative electrode to the positive electrode. The temperature at which this experiment is conducted is 298 kelvins, just like the standard conditions require. The value, the E0 value, is plus 0.77, so therefore Fe3 plus is a good oxidizing agent. The half cell with the greatest negative potential is on the left side of the salt bridge. So we can find the E0 of the cell by subtracting of the E0 of the right hand electrode minus the E0 of the left hand electrode. The left cell is being oxidized, the right cell is being reduced. Let's consider an example of an electrochemical cell made up of zinc and copper. Now, as you can see, the E0 of the Zn2 plus Zn couple is more negative than the E0 of the Cu2 plus Cu couple. So the Zn2 plus Zn compartment has to be placed to the left, and the Cu2 plus Cu compartment has to be placed on the right. E0 of the cell, or the EMF of the cell, is the E0 of the right hand side, which is that of copper, minus the E0 of that of Zn2 plus, the one on the left. So therefore it's going to be 0.34 minus 0.76. It's plus 1.1 volts. To apply the information that we just studied, consider the following questions. What potential difference would be generated by connecting the two half cells? Cu2 plus 2 electrons forming Cu with an E0 plus 0.34. Al3 plus 3 electrons giving Al, E0 equal negative 1.66. As you can see, aluminum half cell has a more negative E0, so it has to be placed on the left, and Cu has to be placed on the right. E0 of the cell is equal to the E of the right hand electrode minus E of the left hand electrode, so it's going to be 0.34 minus 1.66, so it's going to be 2 volts. Another question, this time we are considering Pb and Ag half cells. Pb2 plus 2 electrons forming Pb solid. The E0 is negative 0.13, which is more negative, so we have to place this half cell to the left. And Ag plus electron Ag, the E0 is plus 0.8, so this half cell has to be placed on the right hand. E0 of the cell is equal to the E0 of the right-hand electrode minus the E0 of the left-hand electrode. 0.8 minus 0.13, it's gonna be 0.93 volts. Another example, this time we're considering PB and CU electrodes. The E0 of the PB2 plus PB couple is negative 0.13. This one has to be placed to the left. Cu2 plus Cu is 0.34. This one on the right. The E0 of the cell is equal to 0.34 minus 0.13, and the answer is going to be 0.47 volts plus 0.47 volts. The last example, we're considering zinc and Al. Of course, Al is more negative than zinc. The E0 of Al is more negative than the E0 of zinc, so it has to be placed on the left. So the answer will be E0 of the right-hand electrode minus E0 of the left-hand electrode minus 0.76 plus 1.66, so plus 0.9 volts. That's everything for our second video. Thank you for watching.